Alright, what's up guys? Welcome back to another video. Today we're going to be doing AVL trees, and after sort of doing like a little review on it, I've realized that I might have to make another video for a bigger example on the AVL tree, just in case. So for this video, it'll just be on like the very basic stuff, right? And I'll just sort of like explain it in a simple way. And then afterward, I'll show like a bigger example, just in case for viewers who don't understand everything. So this video is just on everything like the basic stuff. Okay, so in a way, think of AVL trees as like an advanced BST, so like advanced binary search tree. And so let's first think like, why do we even need AVL trees, right? So the thing with like a normal BST is that there's sort of like a problem. In the best case scenario, that's base. In the best case scenario, it means that the tree is basically balanced, correct? So when that happens, the height, or h, would just be around log of n. And then when you do like search, insert, or delete, they're also just basically big O of log of n. But that's the best case scenario, and that's for like a balanced tree. However, on a normal binary search tree, there's also the worst case scenario. Worst case. And with a worst case scenario, the tree becomes sort of like a linked list, right? So let's say a tree looks something like this. When that happens, the height becomes, it just becomes n. And so when you do search, insert, or delete, it will be big O of n instead of log n. So basically, a plain binary search tree, BST, can degenerate. So what an AVL tree does is it's a BST that keeps itself balanced as you do insert and delete. So this way the height stays big O of log n even in the worst case scenario. So AVL tree keeps BST balanced. Basically, it's trying to keep the BST in the best case scenario as much as it can, right? Okay, so now let's just quickly define what exactly is an AVL tree. So like I mentioned, an AVL tree is a self-balancing binary search tree where for every node, the heights of the left and right subtree is differed by at most just 1. And so there's this thing, which I will also explain what it is. It's called balance factor. And so for every node n, balance factor will do something like you want to find the height of the left subtree minus the height of right subtree. There we go. So, and then for an AVL tree, the binary factor is always going to give you either -1, 0, or +1, or +1, you can say. So if inserting or deleting a node makes the binary factor right here go outside the range, so for example like -2 or +2, then we have to rebalance it with this thing called rotations. And so it was still, so in a way, an AVL tree is still BST, which is left node and then right. But there's sort of like a extra height balance condition. Hopefully it makes sense. If it doesn't, I'll show examples. So, if you don't understand, that's fine. Okay, so just the idea of sort of like the height and balance factor. For every node, or for any node, we have height of the node is going to be equal to 1 plus the max of either height of left or right. Right. So let's say the height of the left is like 2, while the height of the right is 3. Then we want to find what the max is. The max between these two is 3, and 3 plus 1 will mean that the height of the current node is going to be 4. There we go. And then we have the balance factor, and I'm just going to call it BF. Again, it's going to be the node, and then that's going to be the height, or I'm not going to write the whole thing. Height of left minus the height of right. So like right here and right here. And what you should get is not what you should get, but more like what you want to see is that you want to get an answer that is either -1, 0, or +1. Okay, so if you see, like, for example, if you get balance factor is equal to +2, right? That means the left side is too heavy. If you get -2 or -2, that means the right side is too heavy. And so when that happens, we want to do this thing called rotation. And what that does is it's going to change the +2 and -2 into one of these, or -1, -1, +1. Okay? All right, so I'm trying to think if I should do the rotation first, or should I explain the balance factor? Let's do the rotation. Okay, so we'll come back to this one, and I'll keep it here because I will re-show this when it comes to showing examples. But let's just get the very core idea of rotations. So like I mentioned, rotations. Like I mentioned down here, not down here, but yeah, something like this. Oh, I don't know why I deleted that part, but right here, if you get balance factor of either -2, -2, or +1, then you have to do rotation. And there are 4 cases. So and just to tell you, rotations are how we're going to repair the tree shape. So this way it keeps the BST in order. So there are 4 cases. Rotation, 4 cases. It's called LL, RR, LR, RL. Okay, so what LL basically means, left, left. I'm not going to write it down. Left, left. That means it's heavy on the left side. So you want to do the opposite of what the left means. Do a R, which is a right rotation. If it's RR, then that means it's heavy on the right side. And when that happens, you want to do the opposite, which is a left rotation. If it's LR, that means left child heavy on its right side. And when that happens, you do exactly the letter LR. So you want to do a left rotation into a right rotation. And then same for the RL. You do a right rotation into a left rotation. So I will obviously show an example. So let's say you have a unbalanced tree that looks something like this. So just by looking at it, you can kind of notice that this is a left because we have a left here and then another left here. So this is basically unbalanced. So when we see left, then we have to do this rotation, which is a right rotation. And how the rotation works, it's sort of like, think of like you're doing a pulley. You have something down here with a line, and then you have the pulley over here. And you as the person is trying to grab this rope and try to like move this thing up higher, right? And what it does is you can kind of see that it's making sort of like a curve in a way. So you want to do the same thing with the node over here. You want to do a curve, and as you can kind of see, it's going towards the right now. We're doing a right rotation. So when that happens, you just pretend that the Z can move downward while the L moves up, and then the X moves up. So when that happens, you get Y over here, Z over here, and X over here. Notice how compared to this, which is a linked list, this right now looks more like a tree. And so after a right rotation at Z, you have a balanced tree. So when that happens, Y becomes the new root of the subtree. X is still on the left of Y, and Z is still on the right of Y. Look over here. This node right here, Y, what's on the right of Y when you go up? It's Z. And so when you do the same thing here, it's the same thing. The right of Y is still Z. And so the BST order is basically the same. All right, so now we did the LL. This is the LL case, by the way. Let's do an RR case. So RR case would be, again, the kind of like the mirror side. As you can kind of see, we have a right here and then another right here. This is unbalanced. So what you do is you do a left rotation. So left rotation, it's going to do a rotation this way. Again, think of it as like a pulley. You're just going to pull this thing down, pull the Z down, move the Y up, and move the X up. So like this, like that. So what you will get will be Z on the left, Y on the top, X on the right. Again, BST order is still, preserved. So there's that. Now let's do a LR case. So an LR case would look something like this. Yeah. So you can kind of see we have a left and then a right. See that? And again, this looks like a linked list. So once again, it's unbalanced and you want to make it balanced. What you do is you have to do the exact same letter as what the LR is. You want to do a left rotation into a right rotation. So what that's going to happen is you want to first go over here, do the left rotation first. So do the Y and X this way. So again, Y is going to move down here. And then the X is going to be here. And then nothing happens to the Z. See that? So again, when you look at it, what is the right side of Y? The right side of Y is X. Same over here. The right side of Y is still X. Now you do the right rotation. And since the right rotation looks exactly like this, you basically do the same thing. But because I wrote it like this time the X is the root, while the Z is on the right side and the Y is on the left side. That's how you do the LR rotation. And that's how you also identify it, basically. Now, obviously, the RL is the other way around. It will look like Z here, Y here, X here. And look, you have a right into a left. See that? All right, so for this one, you do a right rotation, which is this way. Oop, sorry, let me write it better. This way. And so it looks like Z, Y, X, and then you do a left rotation. So it becomes Y on the top. Oh, sorry, not Y, but X. Boop, there we go. So X on the top, Y on the right, Z on the left. Okay, so this is basically how the rotation works. And so, yeah, that's kind of it. Nothing else really. Just keep in mind. Oh yeah, that's right. I gotta do explain what the balance factor means. Okay, so let's work on the balance factor. Okay, so basically the balance factor is going to be there to sort of like help you understand if a certain side of the node is like unbalanced or not. And once it shows you like sort of the answer, you can determine if it needs a rotation or not. Okay, so let's do a quick example. Let's take this tree. as an example. And we want to compute the height from bottom to up, right? So look over here at the node 1. Node 1 left child. Node 1's left child is null. And so when that happens, that means the height is 0. The right child is also null. So the right child is also, so left, right child, their height are both 0. Okay? And like I mentioned, we want to use the height formula, height node, which is 1 plus the max of height from left and right. And so height, we have the node is going to be equal to 1 plus max height left and height right. This is a balanced tree, by the way. Just putting that out there. Okay, so what's the height left for node 1? So node 1 equals 1 plus max. The height of left is null. Null means the height is 0, so it's 0 here. Same thing with the right side, 0 here. And the max of between 0 and 0 is still 0, but 1 plus 0 is going to be 1. That means this node over here has the height of 1. Okay, now let's look at the balance factor, BF, of node 1. The balance factor of node 1 is 0 and 0 minus 0, which gives you 0. Because, as we look at here, all we're doing is we're the balance factor of the node, we just want to figure out what the height from the left side minus the height from the right side. And keep in mind, you have to do left minus right. You cannot do right minus left. Okay, so keep this in mind for BF. All right, so now we got the balance factor of node 1. So let's put a 0 right here. And we already know the height. Okay, so now let's do node 2. Boom, 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 boom. There we go. Okay, so let's look at node 2. What is the left child of node 2? It's 1. It's the node 1. And it gives you that node 1 has the height of 1, right? And what about the right child? The right child of node 2 is also null, so that means the height is 0. So when that happens, you want to find the height of node 2, right? So the height of 2 is going to be equal to 1 plus the max. What's the height for left? The height for left is 1. What's the height for right side? Height for right side is 0 because it's a null. So what's between the max of 1 and 0? The max is 1 plus 1. And so you get the height of node 2 being 2. So h equals 2. What about the balance factor? Balance factor is just left minus right. And we already know that the height, by the way, it's height of left minus height of right, okay? So h, there we go. And so the height of 1 minus 0, and you get 1. So the balance factor for node 2 is 1. All right, so what about node 4? You can kind of see that node 4 is the same as node 1. Both left and right is pointing at null. So when that happens, you do the height of it for node 4, 1 plus the max from left and right being 0. So the height of node 4 is 1. And so you can kind of see, even though these node 4 and node 2 are in the same level, however, their height is different, with node 4 having the height of just 1. Now, what about the balance factor? Balance factor is 0 minus 0, which gives you 0 for node 4, and so node 4 has 0. Now, let's look at node 3. Node 3 left child has left child height is 2. From here, so node 3. So the height for node 3 is 2 on the left side, and then on the right side is just 1. And so looking at it, what's the max between 2 and 1? It's 2 plus 1 equals 3. So for node 3, the height is 3. What about the balance factor for node 3? It's just, 2 minus 1, which gives you plus 1. That's right. It's plus 1 here as well. Sorry. Don't put just 1. you have to write it out if it's like a positive one or a negative one. If it's a positive one, you have to write out +1. That's a mistake I didn't do, but there we go. +1. And that's sort of like, so the tree with balance factor would look something like this. If you also ignore the null. I'm writing all these null down just to have a clear visualization, sort of. Okay, so now you can kind of see that all the nodes have balance factor that is in -1, 0, or +1. So that's a valid AVL. And when you see that none of these have like a +2 or anything, then we don't have to do any sort of like rotations or cases. Even though you can kind of see that, what if you like, you're looking at it and you're like, this kind of looks like an LL rotation, right? LL case. But that's not true at all, because the balance factor is, none of them are outside of +1, 0, or -1. So that means you don't have to do anything, and it just tells you that this tree itself is already balanced. However, if you do see like it's a +2 or like +2 of here or over there or anything like that, then that's when it tells you that the tree is not balanced. So when that happens, you have to do one of the cases. And like I mentioned, for example, if we look over here, the tree looks exactly like this, except we're missing a node 4 here, right? So when that happens, node 1, again, it's going to be height equals 1. And then the balance factor. I keep saying binary factor. Balance factor is going to be 0, just like here. And then when you look at node 2, again, height is going to be equal to 2. And the balance factor is going to be +1. So +1 here. But look at number 3. Because number 3 doesn't have a node on the right side, what's going to happen is that when you write it out, the height for 3, 1 plus the max of 2 on the left, because height 2 right here. And then the height of right side, which is 0. That's just going to show you the same thing. So the height is still there. But for the balance factor, look. Balance factor is the same thing. 2 minus 0. And when that happens, it's outside now. So as you can kind of see, it's a +2. And when that happens, it tells you that this is balanced. And again, just by looking at it, this is a LL case because it's left. So what you want to do is you want to do a right rotation. So it looks like this. You move the 2 here, move the 3 here, and move the 1 here. Now it is balanced. Okay. So that's basically it. Yeah, sorry that the video is a bit long. I just want to make sure I explain everything in detail and that show you what exactly the AVL tree is and the balance factor. In my next video, though, I will definitely show like a bigger example by either getting like a worksheet from online that has a bigger example to do, or I can just create one myself. But yeah, that's basically kind of it. I'm trying to think if there's anything else left for me to really say. And just keep in mind that like, because we're always rebalancing when in nodes like balance factor goes out of range, the height of the AVL tree is always going to be big O of log n. And so operations such as like search, insert, delete, they're always going to be the best case scenario. And then, they're really, you don't really see like even the worst case scenario would be big O of log n as well. So you just need to know that AVL tree does do like extra work to keep it balanced, like the rotations and the balance factor. And so you will think that in a way, when you do things like when you're inserting a new node or deleting a node, they are slightly more sort of like, it just costs more. But you get like guarantees, like a very strong guarantees. And yeah, that's basically it. Yeah, like I said, next video, I'll show examples. A bigger one for, you get the idea. All right, thanks for watching. Bye. if you want to see another side of me that isn't always about computer science, then check out my other YouTube channel and come and watch my Twitch where I play a bunch of competitive games either by myself or with my friends. And not only that, but I do have my Discord available just in case if you wanted to add me either to just talk about anything, whatever you want, or have some kind of question from my video. Thanks.